Any questions? Any questions at all? Okay. Let's begin. Okay. So today I want to do tree-based learning algorithms and boosting. For tree-based learning, we'll give a basic overview of how you can derive a decision tree from data, and then boosting is kind of a very popular, classic, generic machine learning technique, which learns. What does it do? Learns a linear combination of simple rules of thumb to produce a high accuracy final hypothesis. Okay. I don't know how much we'll do for. I don't know if we're going to connect things to online learning very much, but we'll discuss classification and regression trees. We'll discuss weak learners, and we'll go through AdaBoost in some detail. Really, the first extremely popular boosting algorithm in practice. Lots of extremely good experimental results using AdaBoost on a variety of problems. There's now, I don't know, probably well over 70 some odd boosting algorithms, but they all share certain common characteristics. Okay. But before we get to AdaBoost, let's think about tree-based learning algorithms. Okay, so the idea of a tree-based learning algorithm is often with something called a decision tree. We partition the input space into a number of rectangles, and then we have a hypothesis which is just the sum of the, well, essentially we have one value for each given rectangle, and we look and find out what point what rectangle a given point we want to classify on or regress falls in. We go ahead and we predict with that point. That's simply what we're saying here. We're going to divide up our input space into rectangular regions, Rn, and if a point's inside that rectangular region, we'll predict the value Cn. So it's a fairly easy to understand hypothesis class. Keep things simple. Well, our rectangles will partition up all of Rn. So some of these rectangles are infinite, and no two rectangles will overlap. And so this is indicator function notation. So some points in a rectangle, it's 1. Some point it's not in the rectangle, it's 0. So even though you see this sum there, it's easiest to just think about it. Well, what you're doing is you're finding out what rectangle your x falls in, and then the output of your function is Cn, because only one of these terms will be non-zero. So I've drawn these in 2D, but you can kind of maybe imagine this continuing out to infinity, and that continuing out to infinity, and so forth. Here we see here we see two potential ways of partitioning the space. Basically what we want to do is we want to focus on the simple case where we partition our space with a recursive binary partition. So we won't, we can imagine perhaps more arbitrary subdivisions in Rn, but what we'll do is we'll, for instance, here we'll split the space. So for instance, you can imagine that I split the space at T1, that's split into one region, and then a second region on the right. Then I split the space into at T2, that split this region of R1 and R2 in half. Then I split this region here, T3, into R3 and this larger grouping there, and then finally at T4, I split again. So I have this. So the way we'll be splitting our space up is through this kind of recursive binary partition.
Sorry.
Yes.
Was it the left, the right one? What?
The left one is representing a scheme that we won't try to do, whereas the right one represents a scheme which we will do since it has a simple description. Okay. I should comment briefly that besides the notes which are online, the lecture notes follow to a fairly close degree Hasty and Tishbarani. This is this free downloadable text. I also then any other results would be contained in these two papers. I think the boosting approach to machine learning is quite readable, so I also recommend that. But the notes follow and flow the Hasty book. Okay. So let's go ahead and look at alternate representations of those of this plot that I just did. So here you can see that T1, if you recall, was my first partition, and it split the space into two areas. Okay, and so that corresponds the flat perspective. When I split at T1, I created this area, and I created that area. And so representing this as a tree, I see everything to the left is going to be classified one way, and everything to the right will be classified another way. Now, continuing recursive perhaps I then have a split of the region, the area that's smaller than T1 with respect to the T2 variable. So that split my region into these two boxes, and so forth. The other side, I split the x1 variable via T3. That's kind of, you can see that would be roughly now splitting here. Then I split that region again with T2 and T4. And so this is what a recursive binary partition looks like. This is represented as a tree. The other side is a function. I want to point out the fact that this function has this kind of staircase-like nature is just a coincidence of the plot. It made it easier to visualize. That top right region could just as well be quite small. There's no necessary reason for it to kind of appear monotonic. That's just an artifact of the particular arbitrary function we chose to plot. What's consistent is that we have these different regions defined by the splits. Okay, questions so far? So one reason people often like decision trees is it is unlike perhaps a linear combination of Gaussians or a neural network. Depending on what your data looks like, in the first place, the output of the recursive binary tree is quite easy to interpret often, because you can think about, this variable is less than some given value, okay, and then it splits into two classes, and then so it gives you a very easy way to the final hypothesis, it has a nice interpretation. With many types of machine learning, if you can certainly overfit with this. Suppose we keep partitioning. We can keep partitioning until there's one point in every region, no matter what our set of points are, and so we can clearly overfit with this. So it's going to make sense for any way of building a decision tree. There's going to be somehow we're going to want to limit how deep it will finally be. There's notes. Okay. So the question we might want to ask ourselves is, how will we go ahead and build a tree? And how will we prevent overfitting? Okay. So let's imagine we're doing regression. Keep things slightly simpler. Imagine we're doing regression, and our goal is to minimize the square error. If we want to minimize the square error in a given region, and we have a series of points with different y values in there, to minimize the square error, we would just need to take the mean of the y values of those points in that region. So once we have a region, that will define a prediction for us. For instance, with the square error, we could just use the mean of the y values. But how do we choose the rectangular regions? This is the problem facing us. In the best of all possible worlds, we can imagine that somehow we'll say, okay, we'll limit ourselves to a binary partitioning that produces capital N different regions. And so then what we do is we say, well, looking at the space of all capital N possible binary partitions, let's do empirical risk minimization. Let's choose the region which has the minimal square error. The set of regions that have the minimal square error. So clearly, n should be something smaller than m in this format. If we made capital N equal to m, well then, we could solve this problem trivially. As far as I know, in the general case, this is intractable. I don't have a proof to offer for you. I don't know of any exact decision tree learners that solve some variant of this exactly. But a common thing to do is a heuristic, and we'll show the heuristic which people use in practice, which is basically a simple greedy method. So what you can imagine we can do for each potential axis, we can define an pair of axis parallel half planes. Let me maybe describe what this is pictorially. So we want to build our decision tree. Maybe we have x1, x2, x3, x4, x5, x7, x8. And with each of these, we have some associated y value. Maybe I'll draw the y values in red. This is 8. Maybe this is 10. This is 6. This is 15. This is 5, 10. Okay. So here we have a series of points. And the idea of producing a axis parallel half plane is, so let's say this is our x1 axis. Let's say this is our x2 axis. Well, consider splits along the x-axis. How many potential splits are there? Well, we could split and leave no data in a point. We can split here, and we had x3 there. Here we have x1 and x3, and everything else on the other side. Here we have x2 and x3. Here we have x5 and x3, and so forth. Between every pair of points in the x direction, we can go ahead. We have a potential split. So we have different splits. Each of these splits so for each of these splits, we can go ahead and we can calculate the minimum square error. So for instance, I drew one that was easy for me to compute. Suppose we split with this line here. We made this our split. We get these x1, x2, x3 on this side, and x4 through x8 on the other side. Well, to calculate the minimum square error, I would sum these up. I would get 24, so this would give me a mean of 8, and then I'd get 6 minus 8, 10 minus 8, 4, I get something like 8 square error here, and then so forth. I divide this by 5, so, well, I don't know if this is too much detail. So here C1 would be, for this region would be 8. For here, summing up, we have 20, 45. C2 would be 9. I would then go ahead and plug in this C1 and C2 value for this split, and I would see what the square error is. And I would go ahead and I would do this for every possible split. Okay? And then I would simply, if I wanted to choose a split in this direction, I would choose the split with the minimal square error. okay? But rather than just doing it arbitrarily at the x-axis, I would play the same game here. I would go ahead and I'd scan down, I'd choose a split out of the 9 possible splits, and I would go ahead and then choose the split that minimizes the square error, okay? So my goal is to greedily choose a split that minimizes the square error. Yes.
The left portion. The left portion.
You look this up? Okay. So the inner minimization, we just repeatedly find the average. We can find this average. As we scan across, we can cleverly update things, so in any one direction it only takes order m time. I mean, once I create the average here, I can kind of do a clever online changing the average by adding a new point in, taking a point out, and update across. So along one axis, if I have m points, it would take me no more than order n time to compute the square error, and then I need to potentially do this for each dimension, and then I'd simply choose the split that minimizes. And so I can choose one such split and order dm time again, and then with my space now partitioned, I repeat this process. That's all there is to it. So the question, an idea, we know if we continue the process, we'll eventually get each point into a single region. If we don't stop the process, we're going to end up, and we're going to overfit. So things that you might imagine doing is set maybe some maximum depth or some maximum number of splits. Like if I have m data points, I'll only build a tree of size 20%. I only let the tree grow to a certain depth, or I stop splitting after the empirical error works. These are all reasonable things that one could certainly try to control the complexity and use cross-validation with to try to come up with good splits. But through a lot of people have looked at growing decision trees for a long time, and a more popular process, which seems to work well in practice, is actually to grow a full decision tree. So you actually split the decision tree so you get down to 0 square error, and then from that point on, we go ahead and we prune that decision tree. Okay. Okay, so how does pruning work? Pruning works in the following way. We build a very large tree. This bullet suggested, well, maybe, if you have plenty of data, you stop when there's 5 points in every region. You can imagine going down so that each region has a single point. And then what we do is we go ahead and we regularize our tree. Let me explain the notation so we can see in what sense this is regularization. Well, essentially, C lambda is what we're calling the cost of our tree. Mn, Qnt, when we unfold this notation, is just the square error of our tree. Lambda t is the number of regions. So if our tree in the end has a total of n regions, we pay linearly in the number of regions with a constant lambda. So what happens? Let's go through the notation. So we have our decision tree. Capital T is a subtree of T hat. Basically, it's just the final region nodes on the bottom. Mn is the number of data points in region n. Qn is just the average square error, so M and Qn is just the total square error in that region. We're summing over all regions, so this term is just the total square error. It's kind of very heavy notation, but we're following the hasty presentation, so you can go back and read the hasty presentation. So what happens if we set lambda very small? If we try to minimize this C lambda and we set lambdas very small, what will happen? And on the other hand, what will happen if we set lambda very large?
Small is a lot of regions.
Yeah, if we set it very small, like if we set it to 0, well, we'll just keep our original tree. We won't change anything. If we set lambda very large, we're penalizing for a large number of regions. So I haven't described how we're going to prune yet, but essentially we have some trade-off here. So you just have the normal thing with regularization. So the first term is the so if we make here the number of regions, which in this plot is t, then the error goes down some fashion, and the regularizer lambda t goes up linearly. So depending on what value you set lambda at, this line moves up. You choose something there, or you choose something there. So it's the usual story with regularization. We're trading off error and complexity. Okay. How do we go ahead and prune? Well, pruning we do in the opposite way of building. Okay? So it's easiest to simply describe this pictorially. Okay, so here, if we look at our decision tree, we can ask ourselves, what happens when we prune? Well, what happens is what happens just at a given split point if we rejoin two nodes. When we rejoin two nodes, the square error will go back up by however much it was reduced when we split there. If we rejoin here, this split into two regions, reducing the square error. We rejoin here, the square error also will go up. Likewise, we could prune here, redistribute these points into R4 and R5, and square error will go up. So how do we prune? Well, we prune, we simply choose the pruning such that the square error changes the least. Okay, so we've collapsed one node, and that gives us a new tree. Okay, that new tree, we have our new tree. Then we go ahead and we look at all those potential splits again, and we choose the one that reduces the error minimally. That gives us a new tree, and so forth. So we keep going back up, pruning, until we get a list of pruned trees. Okay, so we have a tree all the way with one node, then a tree with maybe 2 regions, and 3 regions, and 4 regions, which we got by successive collapses with the weakest link pruning, and then we just add on gamma t, and we can use that to then choose a minimizer, and then we can go ahead and set this with cross-validation. Questions how that works?
So which nodes can you collapse? Just the ones which are got leaves directly below them?
No, you can potentially collapse, for instance, here, we can collapse at x4, redistribute. So, sorry, we can collapse any one of, we can collapse at R3 and redistribute these points into R4 and R5.
But if you're collapsing, so you remove say you remove a division that went in that direction, and you've got one's below it that go in the other direction on the other axis, you're going to end up with. Oh yeah, okay, just yeah, fine.
It should all redistribute fine.
Okay. Yeah.
Sorry, when you circled the R3 now, does it mean that you scratch the D3 division but you keep the D4?
Yes. So you're going to have to redistribute points given that.
But you've chosen the T4 in a different situation, so it might not be that great a decision to split it.
You're exactly correct. If we merge T3 in, this may greatly increase the square error, so we'll end up not choosing T3. But in terms of the algorithm that we tried for weakest link pruning, we merge at any possible merge point.
And you check that for all the bottom nodes, or you check it all the way up?
So this will affect everything up to this decision here.
Okay.
It won't affect any of the nodes on the other side. We can do the same thing with classification. So suppose we want to classify into one of K classes. Within a given region, we can define the empirical probability, the label, which is just the count of that label over the number of labels in that region. And we just have a simple classification thing where we classify a point in a given region with the label of maximum empirical probability. So lots of standard packages for building classification trees. What people have found experimentally when building classification trees, this should be one over here. PI, no, should be one over that. Okay. So when we grow the tree, rather than using the square error, we can instead, for instance, since we're doing classification, it makes sense to use a different loss function. It seems straightforward to use the misclassification error, but in terms of combining error from different regions, it seems to make more sense to use either the cross entropy, which is just P log 1 or PK, so it's just the empirical entropy of the probability distribution in the given region. Another loss function is the Gini index. We can see that these both are smooth functions, which are larger than the classification error. So people tend to use cross entropy or the Gini index for growing the tree, but then in the end, if your aim is to classify well, people tend to use the misclassification error to prune. So here's an example of a potential boosting application. So imagine you want to build something to classify email as spam or good email. Moving on to boosting. Okay, so that was our quick overview with decision trees, and now I want to motivate boosting for you. Decision trees will come back into boosting in the sense that very simple decision trees are often used in the context of boosting. Okay, so imagine you have an email. You might say, it's probably spam because it uses the word business in it. And you realize, oh yes, that maybe 53% of the emails that if I use this rule, I get it right 53% of the time if I say business. Maybe if an email has one substituted for I in it regularly, that's another rule which maybe is correct some 55% of the time. So using some sort of relatively simple learning method, you may find that it's hard to find a rule that is correct all of the time. The idea of boosting is to combine relatively simple learners in such a way so that we build a linear combination of these simple learners to correctly classify our data. So the basic problem which boosting is designed to solve is if we have something called a weak learner, which is an algorithm which produces a hypothesis which is correct some percentage of the time, bounded away from bounded away from 50%, so it's just slightly better than average, but there's always some small amount that we're guaranteed to be away from average. And the other kind of underlying assumption in boosting is that these learners are really quite simple, often much simpler than a linear classifier. So they're extremely simple learners, but what we're hoping for is that we can combine these simple learners such that they're all at least somewhat better than 55%. And boosting is a way of converting these rules of thumb into an accurate prediction algorithm. At a high level, the boosting algorithm works like this. We have some system, some Oracle, some computer program that can derive rules of thumb from the data, where we just try to achieve better than 50% weighted error. We keep repeating this a number of times. We combine the classifiers with the weighted majority vote like we did in online learning before, and this is boosting. So the idea of boosting is well, how do we, when we want to work on our rule of thumb, what are the examples which are important to us? Well, we try to build a rule of thumb that works on the examples that have been hard for us so far, okay? And then we'll combine these with weighted majority.
Just a general question. Is it important if the rules of thumb that you provide are correct? I mean, obviously we want to give, like, because we can never tell, it will be probably just associations we find, like for example for the word business.
Yes.
Which might be true in 55% of the data set we have, but in reality it might be 49%. So it's actually not a good rule of thumb. So how bad is the influence of if we provide the algorithm with bad rules of thumbs, I guess?
Okay, so so we're not going to go into all the technical details because there's a lot that would need to be done. But if we provide the rules of thumb meeting certain assumptions, then one is able to show some guarantee on how well it will do on the future data. Okay, so we'll see what these assumptions are, but roughly, what are the assumptions? The rule of thumb that you provide is I don't want to do this too technically, but each rule of thumb you provide is guaranteed to be bounded away from 50% by some small quantity. Okay, and depending on how large that potentially small quantity is, the better that rule of thumb will be. Likewise, so it needs to be bounded away from the thing, and likewise these rule of thumbs really have to be drawn from some simple set. Simple set of rules. So then to more precisely answer your question, you say, well, what if I choose these rule of thumbs such that they're good on the training set but bad on the test set?
Right, so doesn't hold basically the assumption.
Well, the point is, so it'll be done under the normal IID assumption, so you'll have the training set and you won't have access to the test set. So you'll, first when you're fitting these things to to the training set and you've sampled, and if on the training set you fit it with some degree of accuracy, and you're doing this for a bunch of things, it's going to be unlikely that they're all going to, for instance, perform as individual rules of thumb, perform badly on the test set. So basically, you know, the guarantee that you prove, the guarantee that you can prove will hold with high probability. Do you still have a question there?
So your answer is basically what you're telling me, yes, we will choose the weak learners that are good enough.
Yeah, the point is, by just choosing weak learners that are slightly better than 50% with some small bounded guarantee, it sounds very surprising. If you choose enough such of these weak learners, and the weak learners don't come from a complicated class, you're guaranteed to generalize well.
So I guess what I'm asking is, I don't believe that I'll find weak learners. How robust is the procedure against learners that don't satisfy the condition? Because I don't think in real life I'll be able to find the guarantee it's 55% bounded.
So if you can't find weak learners, there's no direct guarantee. There's more robust bounds that depend on the assumption that some of your weak learners aren't going to achieve 50 some guaranteed level of accuracy. Okay.
Sorry to bug you with
No. They're good questions. I haven't given you the technical tools to answer these questions, though. But the situation with weak learners, no different than learning on any other small hypothesis class. If you have some hypothesis class, you can only learn functions of a limited level of complexity. You sample a lot, you sample enough data, your test error is likely to resemble your training error, as long as your underlying class isn't too complex. And the way that works into boosting, here your weak learner is your class which isn't so complex, but you're making it more complicated by taking a linear combination of the learners, so that's kind of building a more complicated class. And then what's mixed into the bound is how much simple rules of thumb are better than 55%. But you know, I can, at the end I can state the theorem and maybe you can ask some questions about it, but I'm not going to be able to prove all the steps involved. So the Boost algorithm works as follows. We have a set of data. X's are our instances, Y's are our labels. We're going to maintain a distribution over examples, which I'll denote with D1I. So D1, I'll associate some distribution for each potential example. Then what we're going to do is on every trial, we're going to fit a classifier using the distribution DT. We'll see what we mean in a moment. This could mean different things, but for us, we'll just try to minimize the weighted square error. Once we do that, we're going to then choose some alpha, which will be how much we weight that hypothesis in our final linear combination of hypotheses. And so we're going to maintain a vector of alphas. one for each hypothesis, and then we're going to update our weights so that we have a distribution over the data. So the algorithm as it runs is maintaining two things. For each t, we get a new alpha. So we'll get alpha 1 through alpha t, which will end up becoming part of our final linear combination of weak hypotheses. And we also maintain, you can imagine in the other direction, d1 ... down through dm, which is our distribution over examples, which basically examples which are hard to learn on, we're going to weight more. So the basic idea is we're going to maintain this distribution D on the training set, and on each trial we get a new weak learner. We put more weights on examples which are hard. The weak learner which we build is we wanted to minimize the weighted square error according to this distribution. So what is so right now, imagine we're just learning a function that's either, one of two classes. So the weighted training error at time t will be, if we didn't weight our training error, it would be just the sum of the mistakes. But now we're going to weight the training error. The dt will be larger for the large examples, smaller for the examples which tend to be correct. Depending on our given weak hypothesis, we'll weight like this. So what does log 1 minus epsilon divided by epsilon t look like? We can think about this as a so as epsilon goes to 0, this is large, and as epsilon goes to 1, well, as epsilon goes to 1, it's small, so when epsilon goes to 1, this is, log 0 goes to negative infinity. Just my plot is pretty satisfactory.
Just like Wolfram Alpha.
Okay, so if we have a given hypothesis whose weighted error is largely correct in a given trial, epsilon t is its weighted error, it'll receive a large weight in the final hypothesis. Otherwise, it'll receive a small weight. The weighted mean error will never be less than 50%, so we don't actually get to the negative infinity. We'll get 1 minus a half over a half, so we'll get a weight of 0 if our hypothesis is 50% correct. So technically, yeah, this can only go to so if our hypothesis is 50% correct, it's weighted. The final hypothesis will be 0. Otherwise, it'll be large. Let's go ahead and take our first break for 10 minutes. And, return back.